All right, welcome you guys. We're going to start our chapter 8 today. And I think it's one of our easiest sections, honestly, the whole semester. Some of the notation can get a little bit weird, so you just got to make sure that you understand what the notation stands for. But other than that, I think you guys are going to find it to be one of the best yet. Okay. All right. So, what we're going to talk about in this chapter is sequences and series. And we're going to start off with the sequence. So a sequence is just a list of numbers that exhibit some sort of pattern. And we can have finite sequences, which means sequences that stop, or we can have infinite sequences, which will have the dot, 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 the ellipses at the end. And that'll mean that that goes on forever. Okay. So let me just kind of give you some examples of some sequences. So let's start off with the finite sequence. So an example of a finite sequence might be 1, 2, 4, 8. Okay, it's finite because it stops. Okay. The pattern that we would be exhibiting here, probably can see it, is we're multiplying by 2 every time. Okay. For an infinite sequence, you could have the same exact numbers, but the only thing that would make it, infinite is the ellipses at the end. So once you see the dot, dot, dot at the end, then that means just assume that this keeps on going forever. Okay. Now, as you can see listed right here, we're going to denote the terms using a with some subscript. So for example, this is the first term. So that would be a sub 1. This is the second term. So that'd be a sub 2, a sub 3, and a sub 4. Okay. So that's pretty much it for sequences. So let's look at some. Okay. Write the first 4 terms of the sequence defined by the nth term. So basically, we're just plugging in 1, plugging in 2, plugging in 3, and plugging in 4. I like to get like my little blanks ready. I know I need the first 4 terms, so I'll get 4 blanks ready. Okay. All right, so we're going to substitute in 1. We're going to substitute in 2 to find the second term. We'll substitute in 3 to find the third, and so on. Okay, so this will get us 1 plus 5. So that's going to get us 6. So that's our first term. 2 squared is 4. 4 plus 5 is 9. That's our second term. 3 squared is 9. 9 plus 5 is 14. And 4 squared is 16. 16 plus 5 is 21. Okay. Now, these graphs off to the right are just to show you the difference between me giving you a function of x and me giving you the formula that'll generate a sequence. So this is really important right in my calculus 2 right now. The domain for this function, the domain would be all real numbers. It'd be negative infinity to infinity, okay? And that's why you have these connected. You'll notice they share the same dots. Like this dot is exactly this one right here, okay? So they have these same points in common. This point is exactly that one, etc. Okay? But we connect the dots for this function of x because the domain is negative infinity to infinity. But we're talking about a sequence and this formula generating the sequence. We don't want to connect the dots because our domain is the positive integers. Okay, so basically whole numbers, except for zeros not included. And so if you were to connect it, what you would be saying right here at 1.5 is, there's a first term, there's a second term, there's a third term, but there's no 1.5 term. That doesn't even make sense, right? We're talking about our domain only being positive integer values, 1, 2, 3, etc. Okay. So don't connect them if you're talking about a sequence. Okay, same directions, find the first 4. Okay, so it's just basically us doing a bunch of math, right? Computations. You can use our calculator to do it by hand, whatever floats your boat, okay? Okay. So you have to do the exponents first. You can't like multiply these two by each other because the order of operations that, please excuse my drunk Aunt Sally, says you have to do the exponents in PEMDAS before you do the multiplication, right? So just make sure you're doing the exponents first. And if you're just plugging in your calculator is programmed to know order of operations, okay? All right, so -1/3 to the -1/3 to the first is still just going to be -1/3. And if we multiply that, we get, sorry, my writing's atrocious. We could just cross cancel the 3's. So just the -1 will survive. So -1 is going to be our first term. And we know that we need 4, right? Okay. All right, so let's go ahead and do this one. Let's see here. So I have to do the exponents first. So I have to do -1/3. For some reason, I can't write a 3 today. There we go. Times -1/3. Well, a negative times a negative equals a positive. 1 times 1 is 1. 3 times 3 is 9. So if I multiply straight across, I'm going to get 3/9, which we know reduces, if you divide by 3, to 1/3. So that's going to be our second term, a sub 2. All right, a sub 3. Now we have to do -1/3, -1/3, and -1/3. So this time, 3 negatives, an odd amount, is going to stay negative. And we just have to figure out what 3 times 3 times 3 is. So 3 times 3 is 9, times another 3, you get 27. So again, if you put a 1 underneath, this is going to get you -3/27. And if you divide by 3 again to reduce this fraction, always reduce, right? Then you end up with -1/9 as your next term. All right, we're going to do the exponents first. So we have to do -1/3 4 times. All right, so an even amount of negatives will become positive. And I like to do it as 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81, and that'll get me my denominator. Okay, again, we're going to put a 1 underneath the 3. So we get 3/81 when we multiply straight across. If we divide by 3's, we're going to get 1/27. All right. Now this particular sequence is kind of special. We call this sequence an alternating sequence because the signs alternate, right? We got a -1, now we got a positive, we got a negative, now we got a positive. And it would continue that pattern because I'm having an even amount of negatives, I'm having an odd amount of negatives, I'm having an even amount of negatives. The next one would be odd, you know? So it's going to alternate signs, okay? Now this alternating sequence wasn't like super blatant because it didn't have this right here. But if you ever see something like this, this is a dead giveaway that you are going to have an alternating sequence. Because we know that if you take a -1 and you raise it to an even, it becomes positive. If you take a -1 and you raise it to an odd, it's negative. If you take a -1 and you raise it to an even, it's positive, right? So if you have a -1 being raised to some power, it's going to alternate in sign. So that's your dead giveaway when you see that you're going to be looking at an alternating sequence. Okay. Write the first 4 terms of the sequence defined by blah, blah, blah. Okay. So the first formulas that we were looking at to generate our sequence are what we call explicit formulas. And those are the best. Those are the ones where you can find the 100th really easily. You just plug in 100, okay? But we have this other type of formula called a recursion or recursive formula. And when you have a recursive formula, you can't get the 100th term without knowing some prior terms. So every term is dependent on previous terms. Now, if you're a computer programmer, you really don't want to use a recursive formula if you can help it, because it's going to slow down your program, how fast it's going to run. So you look for the explicit, but there are times when finding the explicit is actually very hard. We're going to look at the Fibonacci sequence in a little bit. And that one, I remember when I was in school, we found the explicit formula for it, but man, it took a lot of work. And the recursive formula was very easy to see. So it's for a programmer, he might have to, or he or she might have to use a recursive formula because it's just too hard to get the explicit. But the one that we're shooting for is the explicit, because to find the 100th term, you just plug in 100. Whereas with recursive, to find the 100th term, you might need the 99. And to find the 99th, you'll need the 98th. And so it'll have to run through all the previous terms. And I think that you'll see that here, okay? So we're going to find the first 4 terms here. And you're almost probably going to feel like a computer here. Okay. Now you'll notice they get the ball rolling. That's what's different on this one. We're supposed to find the first 4 terms. And notice they gave you a sub 1. They already gave you the first term, in other words. Okay. So that's a good giveaway that you have a recursive formula, because we said to find any term, you have to know a previous term. So we have to find the second term. Okay, so I'm looking at this formula now, you guys. I'm going to be plugging in 2 for all of my n's. If I plug a 2 in for this n, I have to plug a 2 in for that n as well. All right, so we would have 4a sub 2 minus 1, take away 2. All right, a sub 2 minus 1 would be a sub 1. And now you can see why they gave us the first term. I have to plug in a sub 1 right here in order to be able to compute this. So we're going to have to plug in the 3. All right, 4 times 3 is 12. 12 take away 2 is 10. So 10 is going to be our second term. Okay. Now I'm going to use the formula again. I want to find the third term, which means I'm going to be plugging in 3's for all of my n's. So a 3 here and a 3 right there. So a sub 3 equals 4 times a sub 3 minus 1. Take away 2. A sub 3 minus 1 would be a sub 2. So you'll notice in order to find the third term, we need second term. We have a sub 2 right here. We're going to drop them in. So we got 4 times 10 is a sub 2. And then take away 2. So 40 take away 2 equals 38. And that's going to be our a sub 3. And guess what? To find a sub 4, we're going to need a sub 3. So you're probably seeing the pattern here, that it's just going to be 4 times the one before it. So I'll just skip right to it because I think you guys are sensing the pattern. So we're going to go ahead and plug in that number that we just got. Oops, got a little crazy with my arrow there, right there. So that's going to be 38. Ooh, we're getting a little bit too big for me without a calculator. Let's see. 4 times 8 is 32. Carry the 3. 3 plus 12. I think it's 152, you guys. We're just going to go with it. All right, so it looks like it's going to be 150 for the fourth one. Okay, so that's our first recursive one we've looked at. Hopefully you can identify the difference between an explicit and a recursive. Instead of just having n's in the formula, it has a sub n's, which means I can't just plug in a number, I have to plug in a term. And so that's the, and they'll usually give you a term or two to get the ball rolling. So here's a very famous sequence, the Fibonacci sequence. And this one is actually giving us the first 2 terms. So for example, to find if I use this formula, right? And to find the third term. So I'm going to plug in 3, you guys, into this formula for every single n. So that'd be A1 plus A2, huh? So to find the third term, I just have to add together the first and the second term. And I'm going to write down the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, dot, dot, dot. Okay. So you'll notice if I add these 2 together, it does get me the third term of 2. Or if I add these 2 together, it gets me the fourth term of 3. 2 plus 3 is 5. 3 plus 5 is 8, etc. Okay, so that's our Fibonacci sequence. And the reason why this one is so popular is because it's found everywhere, like in nature and stuff. Let me see if I can find this video to show you guys about the Fibonacci sequence. I mean, this girl talks super fast, but it's really cool how much you can find the Fibonacci. Okay, so she's a little crazy and she talks fast, but bear with me, okay?
Say you're in math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling, and you're feeling spirally today, so yeah. Oh, and because of overcrowding in your school, your math class is taking place in greenhouse number 3, plants. Anyway, you've decided there's 3 basic types of spirals. There's the kind where as you spiral out, you keep the same distance, or you could start big but make it tighter and tighter as you go around, in which case the spiral ends. Or you could start tight but make the spiral bigger as you go out. The first kind is good if you really want to fill up a page with lines, or if you want to draw curled up snakes. You can start with a wonky shape to spiral around, but you've noticed that as you spiral out, it gets rounder and rounder. Probably something to do with how the ratio between 2 different numbers approaches one as you repeatedly add the same number to both, but you can bring the wonk back by exaggerating the bumps, and it gets all optical illusion-y. Anyway, you're not sure what the second kind of spiral is good for, but I guess it's a good way to draw snuggled up slug cats, which are species you've invented just to keep this kind of spiral from feeling useless. This third spiral, however, is good for all sorts of things. You could draw a snail or a nautilus shell, an elephant with a curled up trunk, the horns of a sheep, a fern frond, a cochlea, and an inner ear diagram, an ear itself. Those other spirals can't help but be jealous of this clearly superior kind of spiral. Better draw more slug cats. Here's one way to draw a really perfect spiral. Start with one square and draw another next to it that is the same height. Make the next square fit next to both together, that is, each side is length 2. The next square has length 3. The entire outside shape will always be a rectangle. Keep spiraling around, adding bigger and bigger squares. This one has side length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and now 21. Once you do that, you can add a curve going through each square, arcing from one corner.
So something that would be good to look at is make sure we get a couple of these numbers. The next one would be 21, the next one would be 34, etc. But what she was doing is if you'll notice the side lengths of the square, where she started with a square that was 1 by 1, and another square that was 1 by 1, and then the next one was 2 by 2, and the next one was 3 by 3. Let's go back and take a peek at it, okay? So this is the 1 by 1, the 1 by 1. 1 plus 1 gets us 2 by 2, okay? And then 1 plus 2 gets us a 3 by 3 square. And 2 plus 3 gets us 5. So this is a 5 by 5. And 3 plus 5 gets us 8. So this is an 8 by 8, etc. Okay, so she's using the Fibonacci numbers to actually make this spiral.
To the opposite corner. Resist the urge to zip quickly across the diagonal if you want a nice smooth spiral. Have you ever looked at the spirally pattern on a pine cone and thought, hey, sure are spirals on this pine cone? I don't know why there's pine cones in your greenhouse. Maybe the greenhouse is in a forest. Anyway, there's spirals, and there's not just one either. There's 1, 2, 3, 4, 5, 6, 7, 8 going this way, or you could look at the spirals going the other way, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look familiar? 8 and 13 are both numbers in the Fibonacci series. That's the one where you start by adding 1 and 1 to get 2, then 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Some people think that instead of starting with 1 plus 1, you should start with 0 and 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and it continues on the same way as starting with 1 and 1. Or I guess you could start with 1 plus 0, and that would work too. Or why not go back one more to -1, and so on. Anyway, if you're into the Fibonacci series, you probably have a bunch memorized. I mean, you've gotta know 1, 1, 2, 3, 5. Finish off the single digits with 8, and ooh, 13, how spooky. And once you're memorizing double digits, you might as well know 21, 34, 55, 89, so that whenever someone turns a Fibonacci number, you can say, happy Fib birthday. And then, isn't it interesting that 144, 233, 377, but 610 breaks that pattern, so you'd better know that one too. And oh my goodness, 987 is a neat number, and well, you see how these things get out of hand. Anyway, 'tis the season for decorative scented pine cones, and if you're putting glitter glue spirals on your pine cones during math class, you might notice that the number of spirals are 5 and 8, or 3 and 5, or 3 and 5 again, 5 and 8. This one was 8 and 13, and one Fibonacci pine cone is one thing, but all of them? What is up with that? This pine cone has this wumpy, weird part. Maybe that messes it up. Let's count the top. 5 and 8. Now let's check out the bottom. 8 and 13. If you wanted to draw a mathematically realistic pine cone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pine coney things. So there's Fibonacci numbers in pine cones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The leaves are hard to keep track of, but they're in spirals too. of Fibonacci numbers. What if we looked at these really tight spirals going almost straight up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. A Fibonacci number. Can we find a third spiral on this pine cone? Sure, go down like this. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple examples. How about this thing I found on the side of the road? I don't know what it is. It probably starts with pine, though. 5 and 8. Let's see how far the conspiracy goes. What else has spirals in it? This artichoke is 5 and 8. So does this artichoke-looking flower thing. And this cactus fruit does too. Here's an orange cauliflower with 5 and 8, and a green one with 5 and 8. I mean, 5 and 8. Oh, this actually 5 and 8. Maybe plants just like these numbers, though. Doesn't mean it has anything to do with Fibonacci, does it? So let's go for some higher numbers. We're going to need some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count, but they have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 20, 24, 42, 53, 54, 55. I promise this is a random flower and I didn't pick it out specially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something spirally. There's even Fibonacci numbers in how the leaves are arranged on this stalk, or this one, or the Brussels sprouts on this stalk are a beautiful, delicious 3 and 5. Fibonacci is even in the arrangement of the petals on this rose, and some flowers have shown Fibonacci numbers as high as 144. It seems pretty cosmic and wondrous, but the cool thing about the Fibonacci series and spiral is not that it's this big, complicated, mystical, magical supermath thing beyond the comprehension of our puny human minds that shows up mysteriously everywhere. We'll find that these numbers aren't weird at all. In fact, it would be weird if they weren't there. The cool thing about it is that these incredibly intricate patterns can result from utterly simple beginnings.
Okay. Okay, so I told you she talks fast. Really trippy, right? Like now you're going to be at the grocery store looking all your fruit differently or any flower that you pick up. Okay, it's crazy that they have these numbers, all of them. Okay, all right, so I'm going to introduce a new symbol. So if you have your calculator, now's a good time to pull it out and see if you can find the factorial button. So it's a button that looks like an exclamation point. Let me go ahead and pull up the Casio because you guys know that I've been using the Casio 300 FX, I think, or ES Plus. I can't remember. I think that's it. Okay, let's get a big picture going of this guy. You have to blow that hover or click to zoom. Okay, so let me zoom on this guy. Oops, I'm gonna take a picture. I figure this is the one most of you guys are using. Okay, so if you are using the Casio, then you will find the factorial button right here. Ooh, that didn't show up very well. Let's use orange. Okay, it's in yellow right above the x to the -1. There's a little exclamation point. Okay, another calculator that people use a lot, Texas Instruments. I don't know what it's called, but yeah, this is the guy. So if you have this one, then it's a little bit harder to find. So I just want to point it out for people that do have it, because it is a common calculator, okay? That where you're going to find it is you're going to find it under the probability button. As soon as you click on that probability button and you scroll to the right, I think it's 3 spaces, you'll see the exclamation point, okay? So I tried to hit up the calculators that are the most common. If you have a different calculator and you can't find it, just email me, you guys, and I'll let you know where it is, okay? So what this little exclamation point, but we don't call it that, right? We call it a factorial. Oh, darn. Didn't need that with it. Oh, dang it. Okay. What the factorial does is, like, let's say I have 5 factorial. Okay. Then the factorial is going to say, multiply 5 by every number below it till you get to 1. So you got 5 times 4 times 3 times 2 times 1. Okay, and so if you go and you try right now on your calculator and you hit 5 factorial in there, you should get 120 out as an answer. So that'll be a good way for you to check and make sure that you know how to use that. Okay. All right. Now notice that 0 factorial equals 1. That's part of the definition. That's kind of a weird one. So you want to make sure that you know that. Okay. All right. So we already did this one. So we said that just means 5 times 4 times 3 times 2 times 1. And then that gets you 120. Okay. So if you're doing them by hand, I mean, I know you guys have calculators, so this might be old fashioned to even go here, but we're going to get more abstract in a second to where I think we need to do this. So 6 factorial, it could be written as 6 times 5 times 4 times 3 times 2 times 1, but I'm going to write it as 6 times 5 times 4 factorial, and I'm going to stop. So this really is 6 times 5 times 4 times 3 times 2 times 1, if you think about it. So we got our 6 times 5, and then 4 factorial is 4, 3, 2, 1. Now, the reason why we're writing it like that is so that we can cancel it with the factorial in the denominator. And so this just makes our math really quick and easy. Okay, we could probably do it by hand faster than we could put it into our calculator. Okay. All right. So let's just go ahead and practice with our calculator, you guys. Let's go ahead and put 9 factorial divided by 4 factorial, 5 factorial. Let's try it on my iPhone because that's all that I have out right now. Let's see. Okay. Okay, 9 factorial. Holy cow, that's huge. Okay, and then that's going to be divided by parentheses 4 factorial times 5 factorial. Parentheses. I'm getting 126, you guys. And that was me using the iPhone, which is really hard to use. But so I'm just going to check it by hand to make sure it's right. So I'm going to expand the 9 until I get to 5. 9, 8, 7, 6, 5 factorial. And then I'm going to expand the 4 out. 4, 3, 2, 1. And then I'm going to leave the 5 factorial so I can cancel him. He's gone. And I'm going to cancel 4 times 2 is 8. So I might as well cancel that. And I can even cancel the 3. 3 goes into 9 3 times. So it looks like I'm just multiplying 3 times 7 times 6. And that is 126. Okay, I feel a lot better. Sorry, you guys, the iPhone, I got to check myself. That thing's hard to use. Okay, so this one's a little abstract, but if you go back to our concept is whatever the bigger factorial is, you are going to expand that until you get to the smaller factorial and you're going to stop. That way you can cancel it with the 1 in the bottom. Okay. So if we're looking at this one right here, the first question you want to ask yourself is which one's bigger? Well, n is going to be bigger than n minus 1. So we're going to take n and we're going to expand it out. Now, if I wanted to expand it out like all the way, it's going to be n times 1 less times 1 less than that. Keep this process going until you get to 1, right? Okay. Now, I'm only doing that so we get some practice with that. I mean, that's what you do, right? If you have 7 factorial, 7 times 1 less times 1 less times 1 less, right? Blah, 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 until we get to 1. Okay. You're always subtracting 1 away. Now, what I'm going to do, though, is I'm not going to go all the way to 1. I'm just going to stop at n factorial because I noticed that or n minus 1 factorial, because I noticed I have an n minus 1 factorial in the bottom. So now we're going to cross these guys off. So it looks like the final answer is just n. Okay. Given the sequence defined by blah, 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 find a sub 3. Now this is an explicit formula, our best kind, because I can just plug in 3. Notice that this term isn't defined by other terms. This term is defined by n, not a sub n. Okay, so that means this is explicit. So I can go right away to just finding the third by plugging in 3. So I'm going to substitute in a 3 for all of my n's. That's a heck of a lot of 3's, huh? Okay, so inside the parentheses, we have 3 times 3. So we are looking at 9 factorial. And 3 to the third is 27. So we just have to do 9 factorial divided by 27. So I got my calculator out, 9 factorial. I'm going to divide that guy by 27 because I don't want to write down that huge number. And I ended up getting 13,440. Hopefully you got that too, you guys. Make sure you pause and practice using your calculator so you get used to it. Okay, so far we've been focused on sequences, but now we're going to move into the other S word, the series, okay? So a series is simply the sum of a sequence. So instead of there being commas between each one of the terms, there's going to be a plus sign between each of the terms, okay? And this would be an infinite series because it has the ellipses, the dot, dot, dot at the end. If I was only going to add like the first n terms, that would be a finite series. And we would call that the nth partial sum. You're calling it a partial sum because you didn't add everything up, right? Like for example, S sub 8 would mean add up the first 8 terms. S sub 7, add up the first 7. So it's a partial sum because really this thing has a dot, 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 but you're going to decide to chop it off somewhere and just add those terms, okay? Now we often use summation notation to write these because, man, it could just be really annoying to have to write this out. So you'll notice this notation helps us to write it pretty quickly. I mean, this notation stands for this, okay? So this is the Greek letter sigma, capital sigma. There's a lowercase sigma too that looks like this. And so the capital, whenever you see the capital letter sigma, it's kind of like our capital S, then that's going to mean sum. In all instances, that means the sum. That even outside of like what you would think would be like a math instance, I always like to pull open Excel and show people that Excel has the sigma. Let's just do a blank workbook. Excel has the sigma right here, and notice it means sum. Like for example, if I were to type into these cells some numbers and then I highlight those cells and then I click on the sigma, guess what it's going to do? It's going to add them all up. So this number, or I mean, this symbol in mathematics is reserved to mean addition, at least the capital S, the capital sigma, okay? As a side note, you're not going to see this here, but we could do the same thing and we could use capital pi, which is kind of like our P for product. So when you see this, it's not going to mean add everything, it's going to mean multiply everything. So instead of there being plus signs between each term in the sequence, there would be times signs between each term in the sequence. So these symbols, all mathematicians have kind of agreed that, hey, we're going to have these stand for certain things such as, you know, summing or adding, and product, which is multiplying. Now, the bottom number below sigma is going to be the first number you're going to plug in. It's not always 1. It could be 0. It could be 2. It could be whatever. But that's going to be the first number you're going to plug in. So let's say it was a 3. If you plug in a 3, the next one you're going to plug in is a 4. The next one you're going to plug in is a 5. And you're just going to keep plugging them in until you get to the top number and you're going to stop. Now, this is a finite series because the top number is a number. This is an infinite series because the top is infinity. Okay, so that means, hey, do it forever. Okay, so write the terms for each series and find the sum. Okay, so this is a finite series. The first number that we're going to substitute in is 1. Okay, so we're going to plug in a 1. And we know to put plus signs. You just got to know because of the sigma, right? It's implied there. We're going to plug in a 2. And hopefully you can tell me when I'm going to stop. The top number is a 3. So that is the last one I'm going to substitute in. Okay, so let's get these values. 3 minus 8 is negative 5. 6 minus 8 is negative 2. 9 minus 8 is 1. And so we're going to be adding this up. So it looks like this is going to be negative 7 plus 1. Looks like we're going to get negative 6 for this. Okay, the first thing that we're going to substitute in is a 1. Plus, oops, sorry guys. I don't think I need this parentheses. I'm going to erase it. There we go. Plus, next thing I'm going to substitute in is a 2. The next thing that I'm going to substitute in is a 3. And hopefully you notice that I'm going to stop at 4. Oops, why did I write an equal sign? I don't know. Okay, so 2 times 1 is 2. 1 squared is 1. So I'm just going to write that as 2, you guys. 2 times 2 is 4. 2 times 2 is 4. 4 over 4. I'm just going to write this as a 1. 2 times 3 is 6. 3 times 3 is 9. That reduces to 2/3. And then 2 times 4 is 8. 4 times 4 is 16. 8 over 16 reduces to a half. Okay, so I'm going to go ahead and add this up, you guys. Again, you can use your calculators, whatever. So this is going to be 3 plus 2/3 plus a half. I'm going to put a 1 underneath, get common denominators. So it looks like 6 is the least common denominator. So I'm going to multiply by 6's. To turn this into a 6, I would need a 2. To turn this into a 6, I would need a 3. So I have 18/6 plus 4/6 plus 3/6. So that's going to be 22, 23, 24, 25/6, I think. Hopefully those of you that do it with the calculator can verify that that's right. Okay. Well, this is our first one where we're not starting at 1. I'm glad that they threw 1 in like this. So the very first thing we're going to do is we're going to substitute in a 3. So 3 plus 1 is the exponent, and 3 times 3. 4 plus 1 is the exponent, and 3 times 4. Where am I stopping at? 5? Okay. So 5 plus 1 is the exponent, 3 times 5. And we're done. All right. So this is going to get us -1 to the fourth. I almost said second. 3 times 3 is 9. This one is -1 to the fifth. 3 times 4 is 12. And this one is -1 to the sixth. 3 times 5 is 15. A negative raised to an even is a positive. A negative raised to an odd stays negative. A negative raised to an even becomes positive. So we are looking at 9 minus 12 plus 15. I'm thinking that's 12, you guys. Yeah, sounds about right. Okay, so we got 12 for that. So at this point, I'm just hoping that you feel comfortable with the notation. It is new notation, and that you understand how to use it. Now, I've thrown this one in here because this one's kind of a weird one. You know, it doesn't fit the same exact situation as the last because there's not really a place for me to plug in 1. There's no variable, it's just a 10. So if that's the case and there's nowhere for you to plug in like 1, plug in 2, plug in 3, plug in 4, then it's just going to be a 10. So like the first term is going to be 10 when I plug in 1. When I plug in 2, it's still going to be 10. When I plug in 3, it's still going to be 10. And then when I plug in 4, it's still going to be 10. So you'll just get a constant 10, 10, 10, 10. So the answer to this would be 40. So that was just a weird one. We got to make sure we do that one. Okay, quite often in my Calculus 2 class, we do re-index things for our series to like maybe make it look more like a P-series or something like that. And it's just good to know that there are different ways to write these because you might like look at your neighbors because you're checking with each other and you're like, oh yeah, we have different answers, but really you don't have different answers. You actually have the same answer. And so that's what this is just going to show you. So for this one down here, you're going to plug in 1 first. You're going to plug in 2. You're going to plug in 3. And so I plug in a 2. You're going to plug in 3 and you're going to stop at 4. I'm not going to do the math. I'm just going to leave it like that because we just want you to see that these are the same. Okay. So for this first one, I'm going to plug in 0. I'm going to plug in 1. I'm going to plug in 2. And I'm going to plug in 3 and stop. And you'll notice 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. And 3 plus 1 is 4. You get a complete match, the exact same thing, even though this looks so different. I mean, it can't look any more different, right? It's different here. It's a different lower limit. It's a different upper limit, okay? So it definitely looks like it's not going to be the same, but it turns out it is. Okay, same thing with this one. If we substitute in 2 first, we get 2 minus 1, 3 minus 1, 4 minus 1, 5 minus 1. So that's going to get us 1 squared. This one's going to get us 2 squared. This one's going to get us 3 squared. And this one's going to give us 4 squared. So indeed, these all matched. Okay. All right. Write each sum using summation notation. Okay, so we want to be able to use that summation notation to quickly write this out. So we're going to put our sigma down. Okay. And we're just going to stare at this. I mean, clearly we can tell that the bottom's always 5. So I'm just going to put the 5 in there. So it's like, yeah, it's always a 5. But now we need to look at this 2, 4, 8, 16, 32. And we need to see, you know, what is the pattern. Okay. So I noticed that this first one is 2 to the first. This next one is 2 to the second. This one's 2 to the third. This one's 2 to the fourth. And this one's 2 to the fifth. So it looks like it's just going to be 2 to the nth, with n starting at 1, going all the way to 5, right? 5 is where we stop at. So we start at 1 and we go all the way to 5. So I'd say this would probably be what most people would write. There's other ways to write it, but I think that one, you know, is probably what most people would write. Okay. So if we take a look at this one, it's very similar to what we just had, but we have to think about these numbers and how to write them. I mean, I can tell that this one is 2 to the first, 2 to the second, 2 to the third. 1 might not be so obvious, it's 2 to the 0. And 1/2 really might not be so obvious that it's 2 to the -1. But there's our pattern. Now, I would accept this a sigma starting from like I equals -1 to 3. But I will say I very rarely see negative numbers used as the index, okay? So if you wanted to still start it at 1, let's just see what that would look like if we started it at 1. So if we started it at 1, we'd have to compensate the exponent. We'd have to, you know, finagle it so that we would get -1 when we plug in 1. So I think if we use I minus 2, it'll work, but let's just check it, okay? So if I substitute in a 1 as my first, then it'd be 1 minus 2, which would be -1, right? If I substitute in a 2, which would be my second term, 2 minus 2 would be 0. So it really is generating -1, 0. So it's looking good. So this could be, I'll put an or between these. Either one of these could be good representations for that series using sigma notation. Oh, I didn't put the top though, huh? Okay. So if we start at 1, let's count how many terms there are. 1, 2, 3, 4, 5. Okay, so it would go all the way from 1 to 5. And I always like to check stuff. If I plug a 5 in, 5 minus 2 is 3. And indeed, 3 is the last exponent. So we did a good job there. Now this one really makes you think about where to start your lower limit and your upper limit and stuff like that. Okay. So we can probably see that the same numbers are happening, the 2, the 4, the 8, the 16, all that. Sorry, you guys, I lost my charger. There we go. So the top, I think we're good at with 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth are what's going to get us the top. The bottom, 3 to the first, 3 to the second, 3 to the third, and 3 to the fourth. Okay. So it looks like they match, huh? 1 here, 2 here, 2 here. So what that means is that we could write it as 2 over 3 to the n or I, whatever letter you want to use, starting with 1 as the lower limit and ending with 4 as the upper limit. Now, in order to make this alternate though, right, it is negative, then positive, and negative, then positive, right? Okay. I can't just do, or maybe I can just do this. If I put a negative in here, let's see if that works, because sometimes it doesn't end up with a negative on the first term, but let's see if it does. So we're going to plug in a 1. If we plug in a 1, it'd be -2/3 to the first. Well, that means it's going to stay negative. So that's looking good. If we plug in a 2, a negative times a negative is a positive. 2 times 2 is 4. 3 times 3 is 9. Hey, this is looking good, you guys. Okay. Sometimes what happens is you might have to add like a +1 or a -1 to get the negative to occur where you want the negative to occur, but we got lucky this time. Okay, it ended up working on the first try. Okay. And then I'm not even going to talk about this. I didn't give you any homework problems on it, so it's not really a big deal in the grand scheme of things for this class. So I'm just going to leave it right there. All right, so that was 8.1, an introduction to sequences and series. Good luck on the homework, you guys.